The problem we are considering here is as shown here. So it is a linear programming problem in which you have to maximize. So note that it is a maximization problem. So you have to maximize 3x1 plus 4x2 subject to the constraints. So there are two constraints and both the variables x1 and x2 are positive and they are integers. So on the right hand side you will see the graphical representation of this problem. So what black dots you see here, they are all within the feasible region and they are all integers. So these are the solutions which are possible. So all black dots are the possible solutions to this particular problem. As we say, if you use the exhaustive enumeration, then you can find out the function values at all these black dots, and the minimum of that is obviously your solution. For this problem, it is a possible strategy, but for bigger problems, obviously it may not be a good way of handling the problem. So let's apply the BBM or the branch and bound method to solve this particular problem. The first step is to find the real value solution. So as we see here, the real value solution to this problem is x1 equal to 5.5 and x2 equal to 4.5. So that is the solution to this particular problem, and the function value is 34.5. The next we will have to do the branching on this particular problem. So at this point I want you to pause and think, how will you do branching? Okay, so let's see how the branching is done. So your initial solution has got x1 equal to 5.5 and x2 equal to 4.5. I will branch on the variable x1. So x1 is equal to 5.5. So the two integers which are to the left of this particular point are 5 and 6. So as we can see here, this is the real value solution. So to the left of this is x1 equal to 5, to the right of this x1 equal to 6. So the yellow and red zones what we see here, these are the two branches that we are making to solve this particular problem. So the first branch is having additional constraint x1 less than or equal to 5, and the second branch is having an additional constraint x1 greater than or equal to 6, which is graphically represented on the right hand side. So this is x1 less than or equal to 5 and this is x1 greater than or equal to 5. So in addition to the constraints, original constraints to the problem represented by these straight lines, you are having one more additional constraint here. So this is x1 less than or equal to 5 and the other one x1 greater than or equal to 5. So each of these branch, the yellow branch and the red branch, you will have to find the solution to the problem. That is the minimum value solution to the problem. Again, the real value solution to the problem. If you proceed, you will find that for the branch number 1, the solution is x1 equal to 5 and x2 equal to 4.82. So that is the branch 1 solution. The branch 2 solution, as you can see, it is not possible to obtain any of the solutions. So for branch 2, you cannot find a solution because it is non-feasible. So the branch 2 is fathomed because of the reason that it is not having any feasible solution, because it is lying to the right of both the constraints. So our feasible region is given as shown here, whereas the region which is covered by branch 2 is exclusive of the one which is given, and hence you have to discard it. Whereas the other branch, that is branch 1, has got a solution. So it has got a solution which is given by the value x1 equal to 5 and x2 equal to 4.82. 82. So that is the solution that you have got. So that solution would be appearing somewhere at this particular point, x1 equal to 5 and x2 equal to 4.82. So that is the solution that is available. So at this point, we cannot fathom this node because it does not have all integers. The solution is feasible and all variables are not integer. So we have to further branch it. So in this case, x1 is already integer. So no need of branching on that particular variable, but we need to branch on x2. So x2 will branch again on the left side and the right side of this particular variable. So on the left hand side, we are having x1 less than or equal to 4, and on the right hand side, we are having x2 greater than or equal to 5. So you solve the problem with this two domains. So you are having green domain and the pink domain, which are given by the constraints which are defined, and you find optimum solution again within this branch. So you will find another solution and again you will get another branching for this particular problem. So let's see how these overall branches for this problem look like. The branches begin at the first node, which is defined by x1 equal to 5.5 and x2 equal to 4.5, which is shown on the graph as this point, and we divide into two branches based on branch and bound methods logic. First is x1 less than 5, that is the part denoted by this zone, and the other is x1 greater than 6 or equal to 6, that is the right side zone, and out of which the branch number 2 corresponding to x1 greater than or equal to 6 is not feasible because it is lying entirely outside the feasible zone. The only valid zone is x1 less than or equal to 5, which has got a solution corresponding to x1 equal to 5 and x2 equal to 4.82. The point is somewhere here. So this is the solution point for branch number 1. And since it is a non-integer solution, the x2 variable is still a real number, we need to branch further. So we'll apply the logic of BBM method and branch based on x2 less than or equal to 4, which corresponds to the portion which is shown on the lower bottom side or the left bottom side of this figure, and the other one is x2 greater than or equal to 5, which corresponds to the green portion. So these are the two branches that we are making, out of which the left hand side branch, the branch number 3 corresponding to the magenta color zone, we are getting all integer solution x1 equal to 5, x2 equal to 4, and the function value is 31. So this node will be fathomed. The branch 2 which is infeasible is also fathomed, but the branch number 4, which is correspondingly shown here on the branch, has got again a real x1 is real 4.71, and hence it needs to be branched further. So in this way we will continue branching and we'll find different nodes in the process of branching, and at one stage after fathoming we will exhaust all the nodes and we'll get the final solution. The entire tree for this particular problem looks as follows. So our starting node is as given here. Then we have seen in the previous slide the branches corresponding to branch 1, branch 2, branch 3 and branch 4. And as you proceed further, you will find various nodes. For example, the nodes which are drawn with violet boundary, they are all fathom nodes. They are either not having any feasible solution or they are all integer solution. So these are all fathom node. out of these fathom nodes, this particular node corresponding to x1 equal to 3 and x2 equal to 6 has got a function value which is maximum out of all the fathom nodes. Remember that this is an maximization problem, and hence the solution to this problem is x1 equal to 3, x1 and x2 equal to 6, and corresponding maximum value of the objective function is 33. So in this sense, the BBM method can be applied to solving a linear integer programming problem. Next we'll see how this method can be applied to a non-linear integer programming problem.